Guys, welcome back to the next editions of Math Olympiads. My name is Mr. Chai. Don't forget to subscribe and then press on the notification bell to receive the latest videos on Math Olympiads and any other math exploration. Right now, today this is our algebraic problem that we're going to solve. The key objective is to find all the possible values of x that satisfy this expression here. Now, first of all, we are going to, because this problem is quite complicated, so we are going to apply a divide and conquer strategy here, right? So the first step in divide and conquer, we are going to break this one down into a few pieces. The first piece being here. All right, here we can say that the square root of this expression must be greater than the modulus of a here by making sure that a is absolute value. Right now, that's the first condition. Now, next we are going to rearrange this expression so that we can have. Just let me rewrite that. Originally, it was this. And then we can divide the whole thing by this expression here. Now that must be equal to 1. And then by applying a rationalization, we will have x divided by a squared plus a plus 1 here. Right, that will still be equal to a 1 here. And then finally, we can see that we have this. Is equal to 2a. Therefore, x is equal to 2a over a squared plus, okay, so that's what we have. And then from here, let me try to divide this over to two different sections here, so it's easier for me to further our discussion. So from here, we can deduce that x, oops, sorry about that. Okay, we can deduce that x must be less than 2a over a squared plus a plus 1. Right, now that one must be less than this. Of course, in this case, we can make an assumption this is a modulus here. Right, so it must be less than this. And then we know that the square root of this expression, which is given in equation number 1, is always greater than the modulus of a. Since it's greater than modulus of a, then we can further deduce that the modulus of x must be the same as the modulus of this expression, which is actually a 2. Therefore, we have managed to deduce the first conditions that satisfy all the solutions for this expression, which is x modulus of x must be less than 2 here. So this is the second restriction. Right? So I hope that is clear for the first divisions of our problem. Now next we're going to make use of this restriction in the next section of our analysis. Right? Okay. Just let me clear this up. I will write down the major result that we need. So from here, we know that the modulus of x must be less than 2 here. Right? So from here, we are going to come back to the original expressions now. We're going to conquer the whole expression in this situation. So from here we can rewrite this, become this. Okay, so we have a squared plus a plus 1 square root. Now you can square both sides. If you square both sides, okay, so I'm going to write down the step by step so it's easier to follow here. So you can square both sides. If you square this, that is just a squared plus 1 here. And then if you square this, you will get x squared, a squared minus a plus 1, of course. And then don't forget we have 2x a squared minus a plus 1 square root there is equal to a squared plus a plus 1. And then finally we're going to simplify a bit. So from these simplifications, we found that we can reach this expression. Now that is quite obvious. This is 2a. And then we're going to rearrange further because our intention is to get rid of this final square root. That will be 2a minus x squared. Now we're going to repeat the same procedure by applying a square onto the left hand side expression and the right hand side expression. We will end up with 4x squared, a squared minus a plus 1. On the right hand side we have 4a squared minus 4ax squared plus x4 here. And then we can see that we can reduce some of this expression. For instance, 4ax squared, we can simplify that. Now that would only leave us with, okay, we are going to rearrange that. So that will be 4x squared, okay, 4a squared, x squared minus 1. Let me see whether I got that correct. Okay, that is gone. And then the other side will be x4 minus 4x squared, which is the same as x squared minus 4 here. And then finally from here, we can rewrite this as 4a squared is equal to x squared minus 4 divided by x squared minus 1. Alright, now this is the final sections we're going to analyze before we can finalize the solutions here. So I'm going to rewrite this finding. We found that 4a squared is actually equal to x squared minus 4 divided by x squared minus 1. So these are the two major conditions that we're going to consider in the wall. So let me clean this up here. Okay, let's clean this up here. Okay. Right, now from here we know that because a are all real numbers, 4a squared must really means that 4a squared, which is equal to x squared minus 4. So this whole expression must be greater than or equal to 0, of course, initially, right? But due to this restriction, because we have this restriction here, which actually imply that the x is lying between -2 and 2. Therefore, because this is lying in between -2 and 2, this x squared minus 4 would be less than a 0. Okay, would be a less than 0, which indirectly imply the same result here that we have, which is actually less than 2. Now that's the same result that we are getting here. I just want to highlight this. Okay, so not very significant, but we managed to tally our first restriction. Now next, since this one is less than 0, since the top one is less than 0, in order to ensure that 4x squared is greater than or equal to 0 in this case, the denominator, so denominator x squared minus 1 must be less than 0. Okay, so from here, x squared is less than 1, which imply that x must be lying between -1 and a 1. So there are many ways you can actually obtain this. It's either by drawing a graph, for instance. So just a recap on your quadratic analysis. So you can actually draw a graph. This graph here is quadratic graph that cut through -1 and 1. So it's a quadratic graph that looks something like this. We are interested in the sections of the graph that is below the x-axis. So below the x-axis, therefore the x must be lying between -1 and 1 for these expressions to be true. So there's a bit of a recap for some of you. And then finally, yes, we have already reached the final conclusions. Therefore, all the possible solution for x are lying. Okay, just let me finalize that. So conclusion, all the possible solutions. So x are all real numbers such that is a line between -1 or 1 here. Right. And then this will satisfy this expression here. So I hope that is helpful to some of you who are practicing your algebraic skill. Alright. Let's move on to the next problem in a short while. Back to the next problem that we are having is partially an algebraic problem, and then partially is exponential, and then indirectly it could be a logarithmic problem also. Right? So you can see that our objective is to find all the real numbers x for which it satisfies these equations here. Right? Now, first of all, we can actually represent this using an analogy series. For instance, we can actually represent this as ax plus a plus 1x plus a plus 2x, and then equal to a plus 3x, a plus 4x. Alright, so it looks quite similar in this case, where the a is actually 10, and then x are all real numbers. Alright, now using trial and error, of course, this one is not really trial and errors, but in our case, I try to make it simple a bit. I just say that through trial and error, and then we can sort of verify that using trial and errors, a squared plus a plus 1 squared plus a plus 2 squared. So we're going to consider this way. Using trial and error, we can consider the following result. Okay, we can consider the following result here, which is the same as a3 squared plus a plus 4 squared here. Right. Now, by rearranging and simplifying, for instance, now based on my perspective, I would actually do it this way. Okay, so I will do it a squared equal to the a plus 4 squared minus a plus 2 squared, and then the other one will be a plus 3 squared minus a plus 1 squared. Alright. Now the purpose is for me to simplify this quadratic expression. Now by doing so, I would be able to like get myself a 2a plus oops, so plus a 6. So that will be 2a plus a 6, and then this part here I would actually end up with 2a plus a 4. And then by simplifying this, I would be able to get like 8a plus a 12 plus a 8 plus a 20. Therefore, I have obtained a quadratic equations in this form. And then to my surprise, of course it's no surprise here, I found that the solutions to this is actually a 10a plus 2. All right. And then I found that a is actually equal to 10, which actually fit in very nicely with my initial hypothesis. So we know that from this expression, a should be a 10. So by using trial and errors, we try to consider the square of this expression of this equation. And then by solving these quadratic equations, I found that the solution matches the value of a equal to 10, which mean this is a great discovery. I found that the value, one of the value that satisfy, one of the real number x that satisfy this equation is actually a 2. Okay, one of the solution is x equal to 2. Okay, so I hope that is useful. I'm going to write down our first solution. So the first solution, I would say, first solution, x is equal to 2, by using this a bit of trial errors and a bit of analysis and exploration. Now next, let me clean this up. We're going to consider some other solutions if they exist. Right? So to do that, I will need to rearrange this one more time. Check for answer, I'm going to divide everything by 13, 13x. So this whole expression I can write as x divided by 13x plus 11x divided by 13x. As I said, it has something to do with exponential at the same time. Okay. And then what else do we have? 13x divided by 13x is basically just a 1. So 14x over 13x. And then just by describing it properly, I would have this. One plus 14 over 13. Okay. Now the importance of describing it in such a way is not because we are just having fun with division here, but the result on the left hand side and the result that we can get on the right hand side. We notice that if we were to sketch a graph that represent the left hand expression, just a rough sketch here, forgive me if I sketch this graph wrongly, right? Now we will get something like this. So the left hand expression, if we were to sketch a graph, because this is a decreasing function, as 13 is larger than the numerator, so it's a decreasing functions, I may say that that is something like this. It's decreasing. Okay. If I were to sketch a graph that represent the right hand expression, we notice that this one must be increasing. For instance, something like this. And then since one of the functions is increasing and then the other function is decreasing, therefore the only chance that they can meet each other is at one point, which means it will yield one solution. And then the only solutions that we have at this moment is x equal to 2. So by describing it in the exponential form, in this case, with the help of graphical representations, we can conclude that there is only one solution to this algebraic problem, which is x equal to 2. Right. Now I hope that has been useful to all of you. Right. Now I'm going to move on to the next problem in a short while. Right. I'm going to see you guys. This is our last problem for today. Okay. This is another algebraic problem that we are facing here. X cubed minus 3x is equal to the square root of x plus 2 here. Now from this equation, it's quite obvious that we can see that x is greater than or equal to negative 2, or else we will be solving for a complex solution. Here we try to make it restricted to any real numbers then. We are not trying to solve for any complex solution. So we know that x must be greater than negative 2 here, right? Now, because of that, we try to consider two cases here. We are trying to consider case number 1, where the x is actually lying between negative 2 and a 2 here. It'll be easier in this case. By having this, we are going to by having this case, we're going to let x equal to 2 cosine a, for instance. X equal to 2 cosine a, where the a is lying between 0 and a pi. So you can see that when a is equal to 0, that is basically a 2. When a is equal to pi, it will be a negative 2. So this is the representations that we are going to use. For this case, we are going to substitute this into its original expression. So that would actually yield 2 cos a cubed minus 3 2 cos a here. Okay. And then that will be equal to 2 cos a. Is it 2 cos a? Yeah, correct. Plus 2. Okay. Now, the main reason why we introduce this trigonometry representation is because it's one method to get rid of the square root. Right. So in a short while, you will see how this is being done. So from here, we found that we have an 8 cos cube a minus a 6 cos a here. And then from here, we can factorize this as a cos a plus a 1 square root. Right. Okay. Now from here, from the identity of cos 2 theta, so we're going to use one of the very famous double angle identity. So from here, we know that cos 2 theta is actually equal to, hold on, just let me write that differently so that we can refer. So using this identity, we know that cos 2 theta is equal to 2 cosine square theta minus 1. Or indirectly, we can also write that down as, if you are given cos theta instead, we can actually write cos square theta over 2 minus 1. Right. So we're going to make use of this section here in this expression. So by using this, we can write this as 2 cosine square theta divided by 2 here, minus 1, that is actually cos a, oops, because I'm using a different expression here, I should be using a instead. So that will be a. Okay, so there should be a minus 1 plus a 1. So you can see that we can get rid of the negative 1 quite easily in this case. And then that would actually give us, hold on, I think I put the square root wrongly. So So the square root is supposed to be somewhere here, because this whole thing is inside a bracket, and then there is a 2 here. Okay, so that is where it should be. Let me check that one more time. Yes, okay, now we are good. And then from here, the -1 has been removed, and then we only have 2. And then since it's 2 square, we can simplify that as a 2, and then there's a square here, so that will be 2 cos A divided by 2. Okay, so there you have it. This is our expression at this point, cos A. Okay, and then we can further divide that by 2, which will give us cos 3A minus 3 cos A, and then that will give me a cos A divided by 2 then, right? So I hope that is clear. And then from the recollections of just to consider this, for some of you who memorize this, then you will know where this actually come from. We're going to consider cos 3A then. Now, by using a double angle identity and compound angle, we can actually derive this. Okay, we will get, let me try here. We can get cos 2A plus A, for instance. Okay, that will be a cos 2A, cos A minus a sine 2A, sine A here. And then from here, we can rewrite this again as 2 cosine, this is 2 cosine square A minus 1 cos A. This is a 2 from here, I just rewrite here, this is a 2 sine A cos A. So therefore we have a 2 sine square A cos A here. And then by a bit of rearrangement, we have 2 cosine cube A minus cos A. And then from here we can also apply one of the trigonometric identity. We will be able to get 2 cosine A plus another, that will be 2 cosine cube A. So you can see that we have indirectly obtained 4 cos 3 cube minus 3 cosine A here. Now it looks exactly the same as these expressions on the left. Let me check whether this is correct. Yep. And then therefore we can rewrite this as cos 3A. Right. Okay, so I hope that has been useful at this point. Okay. So just let me erase off this section here. Okay. Alright, so that is where we are at right now. So we have obtained this very important discovery. I'm going to use this at the top. So let me clean up the rest. We are still on this case here. Okay. Alright, now from here I can write that as cos 3A is equal to cosine A divided by 2 here. Right. So that is what we have at this moment. And then of course we can straight away say that it's actually 3A is equal to A over 2. Yeah. But to make this more general, the solutions, in order to obtain all the solutions that we need, we will have basically 3A is actually 3A equal to plus or minus A divided by 2 plus 2, I would say 2 n pi if you want to put it this way, it's supposed to be 2n pi, where the n are all integer numbers, positive integer numbers. So by a bit of rearrangement, we will have 3a minus a over 2 is equal to 2n pi, or we could have 3a plus a over 2 equal to 2. Instead of using n, I might want to use a different symbol here, just to separate the possible solutions that we can have, and then making sure I define my m as all real positive integers. And then don't forget, we also know that the a is lying between 0 and a pi, 0 and a pi there, right? So knowing that a is actually between 0 and pi, therefore we are going to try this out. For n equal to 1, for instance, for n equal to 1, we have here 5 over 2a is equal to 2 pi. Therefore, our a will be equal to 4 pi over 5. Okay, and then a, because a is located between 0 and pi, yes, this one is accepted. And then we're going to test for the second one, where we have 3a plus a over 2. Okay, alright, I think I made a mistake here. Just let me clean that up. It should be all integer numbers, not necessarily has to be positive here. I think I made a mistake here. Just let me clean it up. It could be any integer numbers. So let's use the second condition. So let's assume that m, instead of letting n equal to 1 here, I can let m equal to -1 for this second case. That will give me -2 pi. So from here I have 7a over 2, which is actually equal to okay, did I use negative? Okay, sorry, my mistake. Let me correct that. Because I'm using 1 over here, I should be using 1 here also. Sorry. So that would be a 1 here. And then that will give me a 2 pi. And then by solving this, I will get a 2 pi. Therefore, a will be 4 pi over 7. And then I found that this is also within that given domain here. Right? So I'm good with this. And then of course, I can also start with n equal to 0, which I missed out. So n equal to 0, therefore a is actually equal to 0. Because this is a polynomial of 3 solutions, therefore I expect to get a equal to 0, 4 pi over 5, and another one to be 4 pi over 7, which u x equal to, because we let our x equal to 2 cosine a initially, just to recall that. So therefore our x will be equal to 2 cosine 0, which is a 2, and then the next one will be 2 cosine 4 pi 5, and then finally we have 2 cosine 4 pi 7 there. Right, now I will just stop my analysis up to this point. Of course, for those of you who like to explore further for some other cases, there's another case that I did not show here. So for anyone who are interested to explore that, the second case that you might be interested to explore is for x is greater than 2 then. Here I just summarize it. If you actually analyze this, it shows that there is no solution for any x that is greater than 2. Therefore, we conclude that all the solutions that we can have for this that satisfy these equations will be given here. Right? So this part I leave it for you to try out. So thank you very much for watching. As usual, if you like what you are looking at, do subscribe and then press the notifications bell. All right. Thank you very much. I'll see you guys again.